Hey guys, well, I've spent the last several days fine-tuning, tramming, checking the precision math used for spindle runout, tram accuracy, and steps per inch. I wanted to make sure that the machine was as accurate as possible for this video. I'm going to be doing some positional accuracy on the impact tolerant touch probe. You can't blame the touch probe for accuracy if your machine is not dialed in. So let's take a look at how I went about this. Alright, so first what I want to do is I just want to check and see what kind of spindle runout I have. Almost a half a thousandths, maybe. You can see. We can check the inside taper. Let's check it for runout. Okay, so we checked the outside of the spindle. Now let's check the inside taper. You can see how I've got it set up here, hopefully. So let's check what we have here. Get this, there we go. Really good tolerance there. So I'm pretty pleased with that. About a quarter of a thousandths, between a quarter and a half thousandths, I would say. Alright, so I want to check my spindle runout with a piece of stock in here, about the same length as the impact tolerant touch probe, about 4 inches down here. So I want to see what kind of runout we've got. Each one of these marks represents 0.0005 or a half a thou. You can see we're really good on the runout there. Pretty satisfied with that. Considering it's in a drill chuck, which could introduce runout, as well as there's probably some runout in the R8 collet, but it seems to be pretty good compared with the spindle measurements. Pretty happy with that. I'm going to tram my spindle, make sure that it is as close as possible. Now I've got a indicator here with about a 6-inch swing. Yeah, about a 6-inch swing here. And let me see if I can get this. I'm set on 0 here. I've been working on this already, so don't be surprised when this is when the tram is really close, because I've been working on it for a while. So we're on, hopefully you can see that in the camera, but we're on 0. And then I'm going to spin this around. And check it over here, and you can see that we're really close to 0. So I'm pretty satisfied that the head is square. Also want to tram the Y direction, make sure that it is okay. Of course I can't go but about 6-inch swing here, but see we're within a thousandths on the Y and the X. Alright, so now that we've got that trammed, we can indicate our ring here. Today I am going to check my positional accuracy using the offsets in the offsets tab. And what I want to do is I want to first of all get a baseline and see what type of accuracy I can do by indicating this ring in G55, then moving the machine around to all of its extents, cycling it and exercising it a few times, and then going back and re-indicating this ring on G56, and then compare what I see what the difference is between the 0 on G56 and the 0 on G55. Then I want to do it again for G57 and then compare the three and see what my positional accuracy is to get a baseline for my machine. Once I've done that, I want to install the impact tolerant touch probe, do a probing routine, and then compare that with what I got as a baseline manually indicating the spindle. Now, I've only got a 1/2 thousandths indicator here to indicate the spindle, so I can only really get in within a 1/2 thousandths, or plus or minus a 1/2 thousandths, I should say. So I could be a thousandths off in one direction or a thousandths off in another direction, or I could be fine. I've noticed that I can't quite get it perfect, but at least I know what range I'm in there. So I've indicated this ring, and now what I want to do is I want to zero this position on the offset tab here. I want to zero this position. Get this turned on G55. So I've got G55 in here, and I'm just going to zero my X, Y, and Z, so I'll know exactly what height I had the indicator. So then what I want to do is I'm going to raise the machine up. I'm going to exercise it through the extents of its travels. Okay, so I exercised it, and now I want to go back down to 0 here. On Z. Alright, and then I'm going to switch over to G56 right here, and then I want to indicate it again and set this to 0. So I'm just going to jog it around and get it indicated, and then alright, so let me get this indicated and then we'll come back. Okay, so I've got the ring indicated again in the spindle, and now I'm going to set zeros on my G56 offset. X, Y, and Z. Okay, and now when I switch back to G55, I'm going to see the difference between this setup on G56 and G55. So let's switch back to G55 and we'll see what we're at. Okay, you can see that we are within a half a thousandths on the X and not quite 2 thousandths on the Y. So what I want to do is I want to write those measurements down. So for X it was minus 0.0005, and then Y was 0.0017. Okay. Now what I want to do is I want to raise it up again. We're still zeroed on G56, as you can see. So I want to raise it up again. There's G57. G56 is 0. I'm going to raise it up, cycle it again, and then I want to indicate it one more time on G57 and compare that with G56. So that'll give me 2 comparisons. Alright, so let me run this through the extents. And now I'm going to re-indicate it. So let me get that set up again and we'll come back. Okay, I've got it indicated once again, and now we're going to make sure we're on G57 and we're going to zero all of our axes. Okay, now when we switch back to G56, we'll see what we have. Okay, so for X, I have minus 0.0012, and for Y, I have 2/10, 0.0002. Now you can see that they just kind of flip-flopped. Right here we had about 1,000ths, 1.0012, and on the Y we have 0.0017, and then we had 5/10 and 2/10. So they just kind of flip-flopped. So I imagine that is all within how I indicated it. But that gives me a baseline for my machine accuracy. So as far as my steps per inch and getting back to the exact point at which I was at previously, that is the tolerance that I'm working with. I think that's really, really good. So within 2 thousandths or 0.0015, I would say. Pretty good tolerance. So now what I want to do is I'm going to set my zeros on G57, and then now what I want to do is I want to install my impact tolerant touch probe. So I'm going to raise this up. Going to exercise the mill. Now now that I have the mill exercised, I'm going to remove this. I'm going to install the impact tolerant touch probe. So let me get that. Alright, so now that I have the impact tolerant touch probe installed, and one thing I want to point out is from previous tests, you want to make sure you indicate the touch probe in the same orientation. You want to have it turned the same orientation every time you use it, because of the contact design, the 120 degree contact design. You will get variance between this position along with this position. So if you indicate it in the same spot every time, you'll get consistent results. I'll talk more about the 120 degree contact design later on. So now that I have the touch probe in, what I want to do is I want to indicate G58 using the touch probe. So I'm going to run my probing routine, and then it's going to zero out G58, and we can compare that with the results that we got manually. Okay, so I'm going to probe this. Okay, now I don't know if I had it quite exactly in the center, and because this is a ring, if I had it too far this way, it may throw this measurement off, so that's why we repeat these tests a couple of times. But you can see that our G58 is zeroed. Our last was G57, so let's go to there. So the X, the impact tolerant touch probe, got exactly the same result as we did manually for G57. Okay, and we were 0.0022 on the Y. So what I want to write down is this is manually 0, and then the difference with G58 impact tolerant touch probe, the X I had 0. Pretty impressive. And the Y I had 0.0022. Okay. Let me go ahead and write this as all zeros. Alright, now we're going to do another probe. Let's do G59, and then we'll compare that with our G58 probe. So here we go, G59. Okay, we're zeroed on G59, so let's go back to G58. I'm not sure that I believe that. G58, absolutely no variance between G59 and G58. Pretty impressive. So the impact tolerant touch probe got the same result 2 times in a row. And I've already proven that with the G55, G56, and G57, I couldn't manually set it up that accurately. So now let's go to G54. I'm going to probe it one more time on G54 with the impact tolerant touch probe, and we'll see if we get the same results. Here we go, G54. All right. We're zeroed on G54. Let's check G59, the last one we probed. Okay, you can see the X, we're 2/10 out. And that's a negative. And the Y is 0. I don't know what to say, guys. That's pretty impressive to me. If you are worried about positional accuracy, you can see that using an impact tolerant touch probe is way more accurate than manually setting it up. It looks like my machine tolerances are plus or minus 0.002 manually setting it up, and you can see that the impact tolerant touch probe will get you within half a thousandths. Let's check G58. It should still be 2. Okay, one more time, let's probe it again on G54. Here we go. See if we can get a consistent result. All right. G54, we're zeroed again. Let's check it with our G59. Still 2/10. Still 2/10. So exact same result as we got the first time. That's pretty impressive. Now this is with backlash compensation turned off. I prefer not to run backlash compensation. As you can see, I have it turned off. But even when I had it turned on, it didn't make much of a difference because my backlash is very minimal. So after probing with the impact tolerant touch probe on G54 and getting the 0 set, we can go back and check all of our other setups and compare them to what we've gotten with the impact tolerant touch probe. So the impact tolerant touch probe we probed on G58, G59, which both are the same, and G54. So we're within 2/10 really, either way on the impact tolerant touch probe. And we manually set up on G55, we manually set that up with the indicator. And you can see we're within 0.002 on the X and 0.7 on the Y. G56, we're 1.5 thousandths on the X and 2.5 thousandths on the Y. And G57, we're 0.2 on the X and 0.0022 thousandths on the Y. Very good tolerances. Now of course we saw the differences between these three manually indicated positions, and of course that's most likely user error. I would rather trust the measurements from the impact tolerant touch probe, because that takes me out of the equation and I feel more comfortable with that. Alright, just wanted to kind of show you the differences between manually and indicating it with the impact tolerant touch probe. Now, if you recall, I spoke earlier about the 120 degree contact design. Now, this is an electromechanical switch, very simple in design, and the contact surfaces are 120 degrees out. Now, most of your low-cost touch probes all use the same contact design. There are three distinct differences between the impact tolerant touch probe and these other touch probes. These three elements go hand in hand to create a touch probe that is far more accurate than other low-cost touch probes. The first being the impact tolerance. The impact tolerance allows for the stylus to be stiffer and have less flex than a self-sacrificing ceramic stylus. Now, you may say, well, other low-cost touch probes have metal stylus as well. That is correct. There are a few out there that have metal stylus. Those that do have some other component internally that is self-sacrificing. You can't have one without the other. But with the impact tolerant touch probe you can, because with the retractable stylus you don't have to worry about damaging any of the internal components. The second element we just mentioned is the stylus. Because of the stylus is not self-sacrificing, you don't sacrifice flexing, which increases your pre-travel variation. And then the third element is the contact surfaces itself. There is a special fluid that comes with the impact tolerant touch probe that allows the contact surfaces not to develop oxidation and give you false readings. All three of these components is what differentiates the impact tolerant touch probe and makes it far more reliable and accurate than any other low-cost touch probe. Now, because of the 120 degree contact design, you're going to get pre-travel variation. We'll call it PTV. This pre-travel variation can range between 2 and 4 thousandths on some of these low-cost touch probe. I mentioned before that you always want to orient your spindle in the same location, because the slightest difference is going to affect your pre-travel variation. Anything in this 120 degree section here will have a variation in the amount of travel the stylus moves before the contacts break. Now, this pre-travel variation, of course, is very good on the impact tolerant touch probe because you don't have the flex in the stylus. Now the impact tolerant touch probe has a pre-travel variation in one direction of 0.0003, so 3/10 of an inch pre-travel variation in one direction. Other low-cost touch probes, the Hallmark SPU40 and some of these others you see on eBay, made by several different people, they have a pre-travel variation, and I just averaged this out, but in one direction of 1.5 thousandths. So you can see the difference there. It's 5 times more accurate than other low-cost touch probes. Now with the test I just performed, this pre-travel variation was compounded because we probed in 2 directions. So the impact tolerant touch probe has a pre-travel variation for external and internal diameters of plus or minus 6/10, 0.0006. Other low-cost touch probes, when compounded, their pre-travel variation is 3/1000ths of an inch. So again, you can see it's 5 times more accurate than other touch probes. There are a lot of things that can affect the accuracy on any machine. You could have machine errors in your axis. If your head is not square, of course, it's going to compound as you probe both sides. When I first started running these tests, I thought my machine was set up correctly, but it was not. I've had, incidents running parts, and so the machine was out a little bit. Getting my machine running as accurately as possible, the results still show that when I manually set the machine up, I was only able to get it back to within, say, a couple of thousandths, depending on how it turned out. It seemed like they kind of flip-flopped, but with the impact tolerant touch probe, I was able to get it within 2/10. That's pretty impressive. So other than machine errors that you have to factor in when you're trying to find your positional accuracy, there's also things like thermal expansion, which, depending on how long your machine's running, how hot the bed, the saddle, all that gets, thermal expansion can play into the equation as well. Now, I don't expect a machine of this caliper with the accuracy to be within microns. I mean, I think that's kind of crazy to think that your machine's going to be that accurate, but I'll settle for within 1/1000ths. So now that I've spent about 10 days or so on testing the impact tolerant touch probe for positional accuracy, very pleased, very satisfied. I've had several hundred probing cycles on the impact tolerant touch probe over the last couple of weeks, 3 weeks. Numerous crashes setting up my probing routines. It is well worth the investment to get to be able to indicate your parts with this type of accuracy. As you can see, manually setting up my machine, I wasn't able to get it as accurate as I could with the impact tolerant touch probe. And in fact, I'm probably 4 times as accurate, 5 times as accurate with the impact tolerant touch probe as I am manually setting up the machine. So I think that concludes all my testing for the impact tolerant touch probe. I'm just going to use it now and enjoy it. So on with the next project. If you're interested in one of these impact tolerant touch probes, I'll put a link in the video description for Hallmark Design Ltd, and you can inquire about the availability of the impact tolerant touch probe. Thumbs up if you like the video. If you're interested in any of my CNC conversion plans, you can stop by the website. Thanks for watching. Please subscribe, and most importantly, be safe.